Hi there and welcome back, and now we'll be moving on to our next topic, which is the actually loaded members. So these members are purely or either in tension or compression, and examples of tension members are cables, some braces of frames, and some members of trusses, and many others. And examples of compression members are columns. The most typical or most intuitive is the building columns. Although in some advanced analysis, a column can also carry additional moments. So that depends upon the situations and the analysis. But typically, when you say columns, it's just an actually loaded member. Okay, and also, some terms for compression members are struts. It's just simply a short link. Okay, that's under compressions, and that's typical in mechanical systems. Okay, so now for the stress, for the axial stress. Now, if I have this member right here. Then I subject this actual member to an external load. Then let's say this is F, right? And then if I cut this section right here, right? So if I cut the section right here, what I see is an internal force distribution. Okay, and this force distribution, depending upon the shape, and if you have a regular shape, then and also if it's near the point of loading, then that's going to be uniform. But if it's not, then this distribution will not be uniform. Okay, so if we take one area right here, okay, so this differential area, let's say delta A. And then we'll take this also this load, delta P. So it's like this. So we have this delta A and we have this delta P. Okay. This is what we call the stress. Okay, at this point. So something like a stress at a point. Okay, so that's why we write the equation, or we write the equation as sigma is equal to the limit of delta A. The limit of delta P all over delta A. Okay, as delta A approaches 0. Okay, However, it is also common to work in terms of average. Okay, so instead of going through these derivatives, it's also common to just simply work with average stresses. Okay, so it's just simply P all over A. Okay, so right here in our lecture handouts, so here's an illustration for the axial stress. So we have the stress distribution, we have this internal force. So it's always remember that when we talk about stress, we refer to internal forces. However, in some problems or in some situations, the external is just simply equal to the internal. But a more precise description is that you have to find this internal force distribution. Okay, so here's the pictorial, and then we have the side view, right? So we're just working with average, and for the positive sign direction, we assume positive stress or positive axial stress if it's in tension, if it's in compression, right? So like this. So if it is in compression, then that's negative. Okay, so another one is in terms of stress distribution. We have here in figure 3-3 that it's not always uniform. So actually that depends if at the point, if it is near the point of loading, like for example this one, and then here is the point of loading. So at this point it's not actually uniform. So right here in this section you see a stress distribution something like this. So it's not uniform. But then at points away or significantly away from the point of loading, then we get a uniform stress profile. Okay, and also that's a different topics when we deal with stress concentrations. So for now, let's just assume, or in our computations, we'll just use a uniform stress distribution. Okay, so next one is axial strain. Okay, so for axial strain, so here is our axial members, and because we have these axial loadings right here, then there's going to be a resulting deflection. So when we say deflection, it's just simply a movement of points. So this deflection, okay, let's say from this point to that point, this is actually a deformation. Okay, so the ratio of the deformation to the original length, and if we talk about the infinitesimal level, that's just simply epsilon. Limit as delta L approaches 0, limit of this deformation divided by the original length. Okay, and then just the same with stresses, then we can just simply work with this formula. Okay, so for the sign convention, if it's elongation, right? So elongation, that's the specific term for deflection resulting from tensile loading. And if it's contraction, then that's negative. Okay, so far we have discussed this, the axial stress and then the axial strain. And this unit, this deflection unit, is actually, this is in terms of linear or length dimensions, and our length is also a linear dimension, so that's a unitless, although sometimes it is expressed in terms of microstrains or percentage, and still many typical units for strains. Okay, so now what's the relationship between the stress and the strain? And so the relationship is just simply given by the generalized Hooke's law, that the stress is directly proportional to, actually we'll write it here, stress is directly proportional to strain. Okay, and then the proportionality constant is this quantity E, which is this is called the modulus of elasticity. All right, so here's our relationship, force deformation relationship. Okay, so here's our stress, and the unit of stress is megapascals, and this is unitless strains. And this one, the modulus of elasticity, this is a property of material, modulus of elasticity, and this is also megapascals. And you can obtain this from the tables. Okay, so in solving problems, actually we need to understand, or we need three. I think we need the three fundamental equations or principles. Okay, so again, in solving problems, we will need the three fundamental principles, and number one is the equilibrium equations, right? And we already know this. And then sometimes if the problem is not enough, or the number of unknowns is much greater than the number of available equilibrium equations, then we need to have I think I'll just write it here. The equilibrium equation must be satisfied. And then the second one is, as I was saying that, sometimes the number of unknowns is greater than the number of equilibrium equations, then we will be needing another set of equations coming from the geometry of the deformations. Okay, so we'll write it here that the geometry of deformation must be described. And the third one is the material force, or yes, I think material force and deformation relationships must be characterized. Okay, so this will be the basis of our equations, the equilibrium equations, and we here from the geometry of deformations we have the compatibility equations, and right here we have the force deformation relationships. Okay, so once you have all these three, then you can I believe you can solve a lot of problems already. Okay, so for the geometry of, or I guess we will discuss this first. So we have this material force deformation relationships, and this is just the relationship between the stress and then the strain. So now let's derive what is the stress. Right, so stress is simply force over area, and the strain is simply the deformation or the deflection divided by the original length. Now if we substitute all this in this relationship, in this Hooke's law, generalized Hooke's law, right, so what we get is P over A, and is equal to E times the deflection divided by the L. So now we can represent this, or we can express deflection as if as a function of this other quantities. So this is P all over A, E. Okay, so here's another set of equations. That's the force deformation relationship. So this relates the forces, right? This deflection, this relates the forces. Okay, so this is force to the geometric parameters. I think the geometric parameters is just L and A, and this one is, this E is a material property. Okay, so that's it. Now, depending upon the type of, or the geometry of the actual members, so if we have a uniform cross section, then this equation will just simply work. You can just apply this equation right away. Okay, so at any section, it's simply because you have the same cross section, then the deflection can be computed using these equations. Now, for composite material, like for example, one is steel and then the other is let's say is brass, and also if we have a multiple points, multiple loading points, like for example right here there's still another loading points. Okay, so this one can be computed using the summation. Okay, so I think we should have this. So that's Pi times Li. So that's PL all over AE, but it's the summation. And if we have a variable cross-section, then we just have to go through the integrations. Okay, so that's for the material force deformation relationships. And the last one is the geometry of deformation. Okay, so for the geometry of deformation, that actually I would like to introduce you to this book by Philpott, right? This is Timothy Philpott, and this is Mechanics of Materials and Integrated Learning Systems. Okay, so right here in one of the pages, there is a table regarding the geometry of deformation, and there is actually a classification. Like, for example, how do you describe the geometry, or how do you put up an equation based on the given situations? So number one is if we have a coaxial or parallel members. Okay, so for example, we have this figure right here. So the loading is right here, and once you apply a load, then we have these two materials. So we have a material, this middle material, and then the exterior material. So once you apply the loads, then both of them, they are actually experiencing the same loads. Okay, so how do you set up the equations? Another one is this. Now, if we have this rigid bar right here, and they are all supported by these rods, so once it's loaded, once the bar is loaded, then they all actually will deflect, deflect the same amount. Okay, so if that's the case, then simply that the deflection at 1, let's say member 1, is just equal to the deflection at member 2. Now, if you have some gaps, like for example, then you just have to make some plus, like for example, the deflection at 1 plus gap is equal to the deflection at 2. Okay, so another class is this axial members connected end to end in series. Okay, so for example, we have this member 1, and then we have this member 2, and if you apply a load, an actual load right here, then you would see that the deflection of the total deflection is just simply this E sub 1, and this is actually this is the symbol that we use, but in the textbook it uses the symbol E. Okay, so that's it. Now, if there are some clearance, then of course you just have to include that in the equations. And one last classification of materials are, for example, axial members connected to a rotating rigid element. Okay, so for example, we have here. Okay, so we have here, let's say we have this rigid bar, and it is being connected right here, and we have this member 1, and then we have this member 2. So if you apply a load, so it's like it will deflect something like this. So we have a deflection from point B, right? So from point B, it will deflect some amount, and then the point C will also deflect a different amount, a larger amount. Okay, so if that's the case, then you just have to apply the similar triangles equations. Okay, so right here in our lecture handouts, we have this. So if we have coaxial or parallel axial members, we also have this and this one. So if you deflect, all right, so if there's a force and then this one deflects, so we have this deflection deflection of 1 and we have this deflection of 2. So since you have the distance from this, let's say from this point, so you have a distance A, and from this P into this point, so that you have a distance B, for example. So the relationship will just be simply the similar triangles. All right, so I guess that's enough, and we'll do sample problems. All right, now we are going to do our first sample problem for this topic. And this sample problem is taken from the textbook by Gier and Timonchenko, Mechanics of Materials. And this is specifically example 1-1. Now, the original problem statement is actually different. But right here, I just rephrased it. So instead of expressing these dimensions in sentence or in words, I just incorporated it here. Okay, and also the given figure is also different. Okay, but nonetheless, it is essentially the same problem. Okay, so our problem is that a short post constructed from a hollow circular tube of aluminum supports a compressive load of 54 kips. Determine the compressive stress and strain in the post. Neglect the weight of the post and assume no buckling issues. Okay, so right here is our tube. Okay, here is our hollow tube, and this is subjected to a compressive force P. Okay, so because of that compressive force, then there's a deflection right here of 0.022 inches deflection. The inside diameter is 3.6 and the outside diameter is 5 inches and a length of 40 inches. Okay, so this is just a straightforward problem because you can just simply use directly the stress equations and then the strain equations. Okay, so let's write it here. So for the solution, let's solve for the compression area. Okay, so solve for area. Okay, so area is just simply pi over 4 of the outside diameter minus d squared minus the inside diameter, the square of the inside diameter. So if you substitute all the values, what you get is pi over 4 times 5 squared minus 3.6 squared. Okay, so this is 9.46 inches squared. Okay, next is, now let's solve for stress. Okay, so stress is just simply P all over A. So right here, the external force, if we cut in sections right here, this external force will just be simply the same as the internal force. Okay, so this is just 54 kips divided by 9.46 inches squared. Okay, so if you do the math, what you get is 5.7 ksi. Okay, so the next is to solve for strain. Okay, so the strain is just simply the deflection divided by the original length. So our deflection is 0.022 inches divided by the original length of 40 inches. So this is equal to 5.5 times 10 to the negative 4, or some common units is 550 micro, that's times 10 to the negative 6 inch per inch. Okay, so again, this is just a straightforward a straightforward problem, and that's it. Okay, so in the next video we'll start with or we'll do another sample problem.